Good morning. In the previous lectures, we discussed about the zeroth law of thermodynamics and first law of thermodynamics, and also discussed about the application of first law of thermodynamics. Here onwards, we will try to discuss about the second law of thermodynamics and the heat engines, and different types of the heat engines we will discuss in this chapter. Before discussing the second law of thermodynamics and heat engines, we have to be very much familiar about two important types of processes, the reversible processes and irreversible processes. While doing all the theoretical predictions and calculations throughout this chapter, we assumes that most of the processes are reversible one, but keep in mind that all natural processes are irreversible. So in order to make our theoretical calculations and theoretical predictions more easy, we will use the concept of a reversible process. A reversible process is a process during which various stages of an operation to which the system is subjected can all be reversed back in the opposite direction and in the reverse order, which is the reversible process. That means if you consider a process and the various stages involved during that process can all be reversed back in the opposite direction and in the reverse order. That means in every part of the process, the energy transferred in the form of heat or work is same in magnitude in either direction, and at every stage of the process an infinitesimal change in any one of its thermodynamic variable brings back about its reversal. That means if you consider a process which consisting of different stages or steps, then the energy transferred in the form of heat or work is same in the forward reaction as well as in the reverse reaction. And also an infinitesimal change in any of the thermodynamic variable will be brought back by reversing the process. So the conditions that must be satisfied for a process to be reversible are: the process must be quasi-static consisting of series of successive equilibrium states. Then only we can reverse a process, and the process must be infinitesimally slow, or infinitely slow means it should be very slow process. And also another important condition that for a process to be reversible is that the energy dissipative effects like friction, inelasticity, resistance, viscosity, magnetic hysteresis, etc. are absent. Also the heat losses to the surrounding by conduction, convection, radiation, etc. are absent. Then only the process are reversible. So these are the four conditions that must be satisfied by a process to be reversible. The process must be quasi-static consisting of four series of successive equilibrium states. The process must be infinitely slow. The energy dissipative effects like friction, viscosity, inelasticity, resistance, magnetic hysteresis, etc. are absent. And also the heat losses to the surrounding by conduction, convection and radiation are to be absent. So to satisfy all these conditions during a process is definitely an ideal concept. So reversible process is an ideal concept. In practice it is hard to achieve, but we will discuss our heat engine and respective engines on the basis of the assumption that all processes involved are perfectly reversible. Now the irreversible process, definitely it is the opposite of the reversible process. That means if the process cannot be retraced back exactly in the opposite direction, then we can say that it is an irreversible process. So during an irreversible process, the energy dissipative effects may be present. That means that some energy will be lost in the form due to the friction or inelasticity, or due to the resistance, or due to the viscosity, or due to the magnetic hysteresis, etc. And also heat loss will not be there in the case of an irreversible process. So there will be some sort of heat loss in the process. And the example for irreversible processes are all natural processes. The examples for reversible process, we will consider the all the stages involved in a ideal heat engine, or the Carnot engine is an example for the processes involved having the reversible conditions. So now, based on these two assumptions, that is the processes may be reversible or irreversible, we can discuss the heat engine before discussing the second law of thermodynamics. So heat engine is a device that convert heat continuously into mechanical work. So engine is any device which converts some sort of energy into mechanical work. So heat engine converts heat energy into mechanical work. It is made possible by internal combustion engine and external combustion engine. That means the heat engine can be classified into internal combustion engine and external combustion engine based on the system in which the fuel is burned. If the fuel is burned outside the engine, then it is called an external combustion engine. Example for the external combustion engine are steam engine and Stirling engine. Then in the case of internal combustion engine, the fuel is burned inside the engine itself. So examples are petrol engine and diesel engine. So now let's see what are the essential components of a heat engine. An ideal heat engine essentially should have three parts. One part is called the source. The source is a heat reservoir of infinite thermal capacity maintained at a constant high temperature. So a reservoir, heat reservoir, which is having an infinite thermal capacity and which is maintained at a high temperature. That means any amount of heat drawn from it or given to that source does not affect its temperature. That is what meant by the infinite thermal capacity. So whatever quantity of heat is absorbed from that source, that won't affect the temperature of the source. The second part is the sink. Sink is another heat reservoir which is of infinite thermal capacity maintained at a constant low temperature. Remember, the sink is at a low temperature compared to the source temperature. So any amount of heat given to it or drawn from it does not affect its temperature, since it is a reservoir of infinite thermal capacity. Now the third part of the heat engine is the working substance, which is a substance through which heat is absorbed from the source and is rejected to the sink. So the working substance absorbs heat from the source and rejects the heat to the sink. So there will be a difference between the quantities of heat absorbed by the working substance, which is usually denoted by Q1, from the source, and there is a heat rejected to the sink, which is usually denoted by Q2, and this difference between these two quantities of heat, that is Q1 minus Q2, is converted into work. So the difference between the quantity of heat absorbed by the working substance from the source and rejected to the sink is converted into the work in ideal cases. So while discussing an engine, heat engine, the important thing is that its construction, that is the different parts of the engine, then the parameter which decides the effectiveness of the heat engine is its efficiency eta, which is defined as the ratio between the amount of heat converted into useful work and the amount of heat absorbed from the source, is the efficiency of a heat engine. Since at the end of each cycle machine regains its original state, the internal energy term is unchanged. That means if you consider Q1 is the quantity of heat absorbed from the source by the working substance, and Q2 is the quantity of heat rejected to the sink by the working substance, then the difference in the heat is given by Q1 minus Q2. This difference in the heat absorbed from the source and rejected to the sink is converted into the useful work in the ideal cases. Now the efficiency of a heat engine is defined by ratio of the useful work done to the heat absorbed, that is W by Q1, which is equal to W is Q1 minus Q2 by Q1, which is equal to 1 minus Q2 by Q1. This is the expression for the efficiency of an ideal heat engine. Eta is equal to 1 minus Q2 by Q1, where Q2 is the quantity of heat rejected to the sink by the working substance, and Q1 is the quantity of heat absorbed from the sink by the working substance. So this is the overall idea about a heat engine. Now we have to discuss about the ideal heat engine and the first built-in heat engine, which is the Carnot engine, that we will discuss in the next lecture. Thank you.